Today on Macaulay Math, we start pre-calculus by talking about functions. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus Lesson 1 on functions. Our goals for today. We're going to recognize and use function notation. We're going to use function notation to simplify the difference quotient. We're going to determine the open intervals on which a function is increasing, decreasing, or constant. We're going to use technology to find relative maximum or minimums, and then we're going to determine if a function is even or odd. This lesson explores the concept of the function. We will review function notation and what it means for a function to be increasing or decreasing. We will use technology to find not only the intervals where the function is increasing or decreasing, but also find the turning points where the function changed from increasing to decreasing or from decreasing to increasing. These maximum and minimum points are called extrema. Let's get started.
Okay, let's start with our definition. A function f from a set A to set B is a relation that assigns each element x in the set A to exactly one element y in the set B. The set A is the domain, which we call our inputs, of the function f, and the set B contains the range, which we necessarily call the outputs. So what are some characteristics of a function? 1. In each element of A must be matched with an element of B. Now, B can be repeated, but you can't have two B's for the same A. Number 2, some elements of B may not be matched with the element of A. Two or more elements of A may not be matched with the same element of B. And an element of A cannot be matched with two elements of B. So that's our characteristics of a function. Let's review some function notation. Our independent variable is our inputs. We usually call that x. When you have plugged x into the function f, we call that our output, and it is our dependent variable because the y value is dependent upon which x value that you chose. Function notation, f of x, the function value is equal to whatever the relationship needed to change the input x value into a y value. Implied domain. If f is defined by an algebraic expression and the domain is not specified, then the implied domain consists of all real numbers for which the expression is defined. As a for instance, when you look at this expression here, this 3x plus 5, since all real numbers produce a defined output value, the domain of this particular linear function is all real numbers. Now, if you had a square root function, then the implied domain would be all values of x that do not cause the square root of a negative number. So a couple elementary examples here on how to use a function to evaluate, and essentially that's just a plug and chug. And so if I say find f of 3, then what we're going to do is we're going to take that 3 and we are going to replace it into the function wherever I see an x. So since the function is f of x is equal to 4x plus 2, f of 3 would be equal to 4 times 3 plus 2, which would be 4 times 3 is 12, plus 2 is 14. Similarly, just because we change the independent variable from a number to a variable expression does not change what we do to evaluate this function. In this first one, we plugged 3 in for x. In this function, we're plugging 3x in for x. So I have 4 times 3x plus 2 is equal to, well, 4 times 3, x is 12x plus 2. These are unlike terms, so that is the least I can reduce that particular expression. All right, the difference quotient. Many of you will be taking calculus in the next semester, and so you will see the difference quotient quite a bit, but it is a further extension of the last two elementary examples that we did in the previous page. The difference quotient is a ratio composed of functions. It is modeled after the slope equation, and so you can think of it as this expression here is my y2, and this expression here is my y1, and this h in the bottom is the difference of the x's, and the difference quotient is the basis of a significant definition from calculus, which we will get to later. But this is a good application of what we did on the previous example. So if I say find the difference quotient and simplify your answer for the given function, the difference quotient was given to us as f of x plus h minus f of x all over h. So I want to do just this expression right here first, this first f of x plus h. And what I'm going to do is, just like I plugged in this 3x into my function, I am going to plug in this x plus h into this x in this expression 2x minus 1. So what I'll get here is 2 times x plus h minus 1. So I have just completed this part. Now the second part says subtract away the function again. If I subtract away the function, that function is 2x minus 1, and that will now be still all over h. So this is my difference quotient. And I need to simplify that thing. So the first thing I want to do here is I'm going to distribute, and I got to do that twice. So I'm going to go 2 times x and then 2 times h. That'll give me 2x plus 2h minus 1. And then to get rid of these parentheses, I'm going to distribute that negative. So I have negative 2x, and then minus a negative becomes plus positive. So I have a 1 there. And that's going to be all over h. And you will notice very quickly that this 2x and this negative 2x cancel. This negative 1 and this positive 1 cancel. And so I end up with 2h over h. My h's cancel, and the simplification of this difference quotient is just 2. Increasing, decreasing, and constant functions. Now, I really like this example because it forces us to first review some different types of notation. It allows us to take some of these very wordy, very formal definitions and relate them to some pictures that I have Desmos examples for. And so let's first talk about this. Over an open interval A to B. And so when you see this notation, a lot of times many of you have seen it as an ordered pair or a point in a coordinate plane. In this particular context, this is talking about an interval along the x-axis from A to B, but because we have parentheses here, both A and B are not included in that interval. So if I come over to this example here, the interval from A to B is all of the values along this x-axis from this blue A to this green B without including them. So everything in between here. A function is increasing on this interval if for any x1 and that is smaller than x2. So if I come back here and I can move my x1 anywhere along here provided that the x2 stays on the other side of it. Because again, when we're talking about our axis, as I go from left to right along the x-axis, things get bigger, and as I go from the bottom to the top along the y-axis, the y values get bigger. So in every instance from here to here, x1 is always less than x2. So if I move it down here, I still fulfill that particular constraint. If I move x1 over here, now x1 is greater than x2, and I no longer fulfill this particular constraint over here. So I need to move that back over there. And so what this says is that a function over this interval is increasing if for any x1 that is less than x2, and again, we see that x1 is less than x2, then that f of x1 has to be less than f of x2. And so right here we can see that f of x2 is indeed less than f of x1. So we can say this red curve for our function is always increasing from A to B. Similarly, a function is decreasing over this interval from A to B if, again, for any x1 that is less than x2, and so we'll come back here, and here is a example of a decreasing function. It is going down from left to right. But the formal definition says, provided that x1 is always less than x2, and it is, in that particular case, the f of x1 will be greater than the f of x2. And so when I look at this diagram, the f of x1 is higher up than the f of x2, so f of x1 is greater than f of x2, and we can see that in this decreasing function. A function is constant if for every x1 that is less than x2, all of these elements of AB, f of x1 is equal to f of x2. And so again, a third demonstration here. This is an example of a constant function. And again, no matter where I move my x1, provided that it is less than x2, those two y values, the f of x1, which is actually underneath the f of x2, they are always going to be equal. Next, extrema, relative maximum or relative minimum. A function value f of a is called the relative minimum of the function f when there exists an interval x1 to x2 that contains a such that any x value between these two x's, a is always less than or equal to any value in between there. So let's look at another Desmos example. And so here I have an interval from x1 to x2. I have this x that has to stay somewhere between x1 and x2, and I have this value a. We call f of a the relative minimum because on this interval from x1 to x2, any value that you plug in, it's either going to be bigger than this f of a or equal to that f of a. And we can see that as long as I go from x1 to x2, f of a is always the lowest possible value. And so even when I make x equal to a, that is the only time where f of x is equal to f of a. A relative maximum is also very similar. The f of a is a relative maximum if between this interval from x1 to x2, there is an a such that for any x between these two endpoints, f of x is always smaller than or equal to that a. So again, what does that look like? As long as this x stays between x1 and x2, the point is always either lower or equal to this a f of a value that we are calling the relative maximum. Using a graphing calculator, Desmos automatically finds relative maximums and minimums. You need only click on the graph where you think the extrema will lie. If you're using a TI-80 series calculator, the maximum and minimum functions can be found by pressing the second and the trace button. All right, next, even and odd functions. A function f is even when for each x in the domain of f, f of negative x is equal to f of x. Graphically, an even function is symmetrical about the y-axis. Now, additionally, if a function is even, and there is the point x, y, there must additionally always be the point negative x, positive y. The graph of any even function is also symmetric about the y-axis. A function is odd when for each x in the domain of f, f of negative x is equal to negative f of x. If a function is odd for any point x, y, the function must also contain the point negative x, negative y. And what that means is that graphically, an odd function is symmetrical about the origin. Now let's take a look at two examples. Determine which of the following functions is even. One is odd and one is either. There is one of each. And so I have one of each of these functions. What is my process going to be? So if I want to determine if f of x is an even, odd, or neither function, what I'm first going to do, I am going to take and plug in negative x in for f. So I have 2 times negative x to the third minus 4 times negative x squared plus negative x minus 3. Now I want to simplify this. And so negative x to the third is negative x to the third times 2 would be negative 2x to the third. Negative x squared is just x squared, leaving me negative 4 times x squared. Positive minus x is negative x, and then I get the negative 3. Now I am first going to compare this result to this particular function right here. Notice I have a sign change right here. I have a sign change right there. These two functions are not equal. Therefore, since f of negative x is not equal to the original function, this particular function here is not even. All right. So then what I need to do is I need to find negative f of x. Now negative f of x is easy. It's just f of x times negative 1. All right, and that's easy. We're just going to distribute a negative to all of these terms. So I go 2x to the third times negative 1 is negative 2x to the third. Negative 1 times negative 4x squared, I get positive 4x squared. X times negative 1 is negative x, and then negative 3 times negative 1 is positive 3, and again is not the same as what I got when I plugged in negative x into f. So this is also not odd. Therefore, this first one is a neither. When I plug this original into Desmos, we clearly see there's no symmetry about the origin. Good that we get the neither out of the way first. Now I am just going to erase here so that we can see, but I would suggest you keep these in your notes. Alright, so I want to do the same thing again. So the first thing that I want to do is I want to plug in g of negative x. Alright, g of negative x. I'll have negative x raised to the third minus 6 times negative x. Now when I reduce that, negative x raised to the third is negative x to the third, and then negative 6 times x is positive 6x. Alright, now, because this thing does not match the original, it is not even. Alright, and so the next thing I want to do is I'm going to make negative g of x. Well, negative g of x is just negative 1 times g of x, which in this case, I get a negative x to the third, and then I go negative 1 times negative 6x. That'll give me positive 6x. And this thing and this thing, they do in fact match. We can see right there that they are the same thing. So this function, because g of negative x and negative g of x are equal, then this ends up being an odd function. All right. We can also see that when we look at this thing, we clearly can see some symmetry about the origin. As a for instance, I can see that the x values have the same magnitude, but one is negative and one is positive. The y values have the same magnitude, but one is positive and one is negative. This has symmetry about the origin. Again, I will just erase here for me to look at h. And so just like in the other three, the first thing that I want to do is I want to plug in negative x into h. I'll have negative x raised to the fourth minus 6 times negative x squared plus 4. When I raise a negative to the fourth power, it becomes positive, and I get x to the fourth. Negative x squared will give me x squared times negative 6 is negative 6x squared, and then plus 4. So when I look at this particular function, after I plugged in negative x, it is the same as the original function. Therefore, this function is even. If I go back to Desmos, we can clearly see that this function is in fact symmetrical about the y-axis. If I could fold along the y-axis, this half would match up on that half. So, in order, the first one was neither, the second one was odd, and the third one was even. All right, final example for the function f of x is equal to 1/3 x to the third plus 1/2 x squared minus 6x minus 2. Use a graphing utility to determine any extrema, determine the open intervals on which a function is increasing, decreasing, or constant. All right, so I am going to go right to Desmos and plug this thing in. So I plugged in the function, and clearly this function has no symmetry. It's going to be neither even or odd. But let's zoom out on my y's just a little bit. Let's go like negative 12 to, we'll say, positive 15 on the y's. There we go. Now we can see everything. And so Desmos allows me to get close and just click on my maximum and my minimum. So in this case, I have a maximum at negative 3, 11.5. So let's write that down first. So my answer to part A is going to be relative maximum at negative 3, 11.5. And then I'll have a relative minimum at 2, 9.333. 2, negative 9.333. All right. Now, part B. Determine the intervals on which the function is increasing, decreasing, or constant. And so when I look back at this diagram here, it is increasing from negative infinity up all the way until I get to negative 3. And then from negative 3 until I get to 2, it's decreasing. And then from 2 up to positive infinity, it's increasing. So we want to do that using interval notation. So my open interval is going to start by saying from negative infinity until I get to negative 3. And then it starts decreasing until I get to 2. But once I get to 2, it starts increasing again and will always be increasing. So I'll also have from 2 to positive infinity. But I want to link these two so that I have both of them. I'm going to use this symbol right here. It is the union symbol. And it is an OR statement, meaning it includes both of them. Now, this function is only decreasing on a single interval, and that single interval along the x-axis goes from -3 to +2. So we'll go from -3 to +2. And again, we are not including the x value or the point, the extrema, at -3, 11.5, or the relative minimum at 2, -9.3. We are only talking about what the function is doing from this point at x equals -3 to this point at x equals 2. All right there, folks. That seems like that's all I have. So the Star Wars fun fact of the day. Everybody knows what these creatures are, but the word Ewok is never spoken in a Star Wars movie, at least so far. Well, that's all I have for you today, folks. Have a good day. Goodbye.